Hi everyone. Let's continue our discussion of thermal resistance and building materials, and we'll practice some of the calculations. So we've already talked about individual building materials and their R values, which represent the thermal resistance. But buildings aren't usually built of one material only. All right. For example, take a look at this home detail, this house detail, and you can see that this wall right here is kind of a sandwich of different materials. It's got sheetrock or gypsum board on the inside. It's got insulation. All right. Then there's some plywood sheathing and an air gap. And finally, there is a layer of brick veneer. Right? So there's many different materials all sandwiched together. How are we then going to figure out the R value of this wall? Well, it turns out to be not that complicated. All right, the total thermal resistance of a wall, or in fact, a roof or a floor or some other construction, all right, is the sum of the resistances of all the component parts. We're literally going to add them all together. All right. So it's important to find this total thermal resistance. Why? So that we can compare two different wall constructions. For example, we can compare alternatives. You can make sure that you're complying with the codes. And finally, they're useful for calculations of heat loss and heat gain, and therefore sizing your mechanical equipment, your HVAC. So your textbook walks you through an example, and it's on page 499, and it says find the total resistance and U coefficient for the wood-framed wall detail before. And here's a picture of the detail. Got it right here. All right. On the inside of the wall, we've got a indoor air film. I'll talk more about that in just a minute. Okay. We've got our interior finish, which is the 1/2 inch of gypsum board or drywall. There's no insulation in the cavity of this wall, so therefore it is just an air space, 3.5 inches of air space. Next, we have this layer right here, which is a rigid insulation board. Then 1/2 inch plywood siding, and finally an outdoor air film. So now that we know all of our different components in this construction, we can add up their R values. Let's take a look over here. Indoor air film, 1/2 inch gypsum board, 3.5 inch air space, 1/2 inch extruded polystyrene board, 1/2 inch plywood, outdoor air film. All right, each of those have an R value, and then you add those together and you get a final number. Your total R value, your total resistance is 5.45. Right? Remembering that U value and R value are reciprocals. All right, we're going to take 1 over R to get the U, which is 0.18. I can hear you. You're saying, but Sarah, what on earth? What is those air films, air spaces? All right, let's take a look. An air film next to a surface actually has the same effect as another building material with its own R value. So it turns out that air motion is slowed to a stop. There's friction between a building material and the air moving around next to it. All right. And so this is how we account for that teeny tiny bit of insulative air that literally sticks to your building materials. All right. The transfer of the heat from the air to the surface and the surface to the air is slowed down a little bit, right with that air film, and this is called surface conductance. Now, the air gap or air space, you will hear these two terms, they mean the same thing. Okay. The air space is a layer of air that's kind of sandwiched or trapped between layers of building materials. All right. And in order to account for the insulation provided by that air. We treat it like a building material with its own R value. All right. Um, that R value is the same for all air gap thicknesses or all air space thicknesses greater than 3/4 inch. All right, if it's too small, there's not enough room for that convection cycle to happen. All right, there's a whole discussion of that in your textbook. But in general, it's about the same for all air layer thicknesses greater than 3/4 inch. All right, there is more R value or more insulative value with a radiant barrier. All right, so that it could be important. And finally, it's important to know that this air gap can't exist by itself. Um, the insulation doesn't happen unless the air is completely still and trapped between layers of building material, and it's got to be part of the total wall construction. So you probably already know that Appendix J in your textbook has a big table of all the R values of different materials. But Table J.2 has the R values of air films and air spaces. So let's take a look because it is a little confusing to read this table, I found. First of all, let's talk about air films. All right, air films are everything in the top half of the table here. All right, everything from here and below is all about air spaces. So there are two types of air films, still air or moving air. Typically, we count everything that's inside, so your inside surface of your wall would be the still air, and the outside surface would be the moving air. So that's pretty simple. And then they've got this horizontal up, vertical, horizontal down. All right. What this translates to, horizontal up is a ceiling in winter. All right. A ceiling is a horizontal surface, not a vertical one, and the heat is traveling up. All right, trying to rise and escape. Vertical, horizontal, basically this is used for walls. And horizontal down is used for ceilings in summer. Now you know. Okay. And then what are these four columns? Well, the left two, this says non-reflective, is air films without a radiant barrier. All right. And on the right-hand side, we've got bright aluminum foil. It's basically air films or spaces with the radiant barrier. And finally, I-P is the imperial units, and SI is going to be your scientific or metric units. All right, so typically in this class and in this country, we use the imperial units. Let's move on to air spaces, kind of the bottom half of this table. All right, again, we've got the horizontal, vertical, etc. It means the same thing, ceiling in winter, walls, ceiling in summer. All right. For the examples I'm going through today, all right, we're going to be working with walls, and therefore our number for air films on the inside will be 0.7. On the air film on the outside, we're going to use an average of 0.1 to 0.3. We're going to use 0.2. All right. That range, by the way, depends on weather and air motion. And for air spaces, because we're doing walls, that value will be 0.9. All right, enough of this theory. Let's try a couple of examples. Now, these examples are coming from an online article called Exterior Wall Insulation. And here's the link here. I've just listed it, but it's also in your module. All right, so you can go ahead and pull that up. Let's take a look at example one at the top. The top left of your slide. And here we have kind of a diagram of a wall. This is the inside. There's the inside air film. Then we have a layer of 1/2 inch drywall or sheetrock. All right. Then our cavity, our wall cavity, is filled with 3.5 inch fiberglass batt insulation. All right. And we've got 3/4 inch rigid insulation board on the outside here. Then there's an air space a layer of brick veneer, all right, and an outside air film. Next, example number 2 here is almost the same. Let's see if you can catch the difference. Okay, we've got an inside air film, 1/2 inch of drywall on the interior finish, 5.5 inches of batt insulation, a 3/4 inch rigid insulation board, an air space, a layer of brick veneer, and an outside air film. So the question here is, given those wall construction and given the table here of different materials and their R values, um, which is kind of a very condensed version of the table in Appendix J of your textbook, can you find the total R value for the wall? All right, so I invite you to pause right now and stop the video and see if you can do this calculation. You're just going to find the R value. Um, Make sure you have the right value for the thickness of material that you've got, and then add them up. All right, time's up. Let's see if you got the same answers as these examples. First of all, example 1, we have these values for our different materials. All right, inside air film, drywall, batt insulation, rigid insulation board, airspace, brick, outside air film, and total R value is just over 18. All right. Notice in the table that was given to you for this particular example, they had slightly different um, numbers than Appendix J in your textbook. For classwork in this course, we're going to stick to Appendix J, but know that these values can vary slightly. All right. Taking a look at example number 2, here we go. It's got almost the same numbers. Did you catch the difference? It was in the batt insulation. We've got 3.5 inches here, 5.5 inches there. That's the difference in using 2x4 studs versus 2x6 studs. So the total R value of the 2x6 wall was 26. The R value of the 2x4 wall was only 18, and you can see there's a fairly large difference there. All right. There are several more examples in this website, and I invite you to take a look and see if you can perform these calculations. Thanks everyone. In this video, we covered how to calculate the total resistance of a wall or floor or ceiling or roof construction.